name is Joseph Connor, and I'm presenting my research on PKU Pitfalls, attacks on PKU-based memory isolation systems that I created in collaboration with Tyler McDaniel, Jared Smith, and my advisor, Max Schuchard at the University of Tennessee. First, an overview of what intra-process isolation is and why we want it. Traditionally, the process has sort of been the atomic unit of security in operating systems, but now intra-process isolation allows us to separate components within a single process. Of course, this improves security because it allows finer-grained privilege separation. However, this has not been widely adopted so far, largely because it suffered from performance as well as some complexity issues in the implementation. However, some more recent research has promised dramatically improved performance using a new hardware feature. This feature is a PKU, or protection keys for user space, which is a feature found on some recent Intel processors. Our contribution is to look at this research and identify challenges and gaps in the current approach. And we come away with two main challenges right now. The first challenge is that researchers and operating system developers may have very different security models in mind when they're developing their code. And this difference can cause the operating system to behave in ways that researchers may not expect. And so this leads into the second issue, which is that commonly used assumptions, things you find in security academic literature, don't always hold up exactly as one might expect in a real-world system. First, some background on the PKU feature. It assigns a 4-bit protection key, so one of 16 values, to every page table entry, and it also adds a new unprivileged 32-bit register called PKRU. This register can be modified with a new assembly instruction, which I'll call write PKRU, and each of the 32-bit bits in this register controls access, read and write access, to the 16 different protection keys. Then a new hardware unit checks the PKRU value against the protection key of the page on every memory access and determines whether or not the access is allowed. And in the event that access is denied, the operating system will typically terminate the process with a seg fault. So since this new register, the PKRU, is unprivileged, user space code is free to modify it using the write PKRU instruction. And this means that on its own, the PKU access controls cannot stop an attacker who already has hijacked control flow. This is because the code in the process may already contain write PKRU gadgets, and an attacker just has to jump to that gadget and can modify the PKRU freely. And once they control that register, of course, they can just grant themselves access to each memory domain as needed. Recently, two papers, ERIM and Hodor, each independently proposed two systems that offer a solution to this problem. At a high level, ERIM and Hodor both divide a process into separate components and use PKU to restrict memory access between the components. Both systems also use different techniques to ensure that there are no write PKRU gadgets available in the process's address space for an attacker to exploit. Now, we also have to ensure that an attacker can't just create new write PKRU gadgets at runtime. So both of these systems are going to monitor syscalls such as mmap or mprotect that could create new executable pages. One way to do this is using setcomp and ptrace syscalls, which allow us to essentially create a monitor process that intercepts certain syscalls and is able to modify their behavior. Or, of course, you can do that just using kernel modifications to hook those syscalls in the kernel. Either way, though, whenever new code is loaded into the process, we're going to scan it for any unsafe write PKRU gadgets. And if it does contain those gadgets, the process can be terminated. In addition, we also have to enforce a policy called write XOR execute, or W XOR X, which just means that no memory in the process can be both writable and executable at the same time. Otherwise, an attacker could just access that memory and write to it and create a new write PKRU instruction. And of course, it would be impractical to intercept every single memory access. So instead, these systems try to intercept just when new executable code is added to the process. Our approach was to examine Linux kernel code, documentation, and developer communications in the context of these PKU-based sandboxes and look for any potential weaknesses. Once we found some possible weaknesses, we tested our attacks on a prototype in a realistic deployment. We used the assumptions that our theoretical attacker has already compromised the untrusted component of the process, and so our attacker is allowed to execute any kind of control flow hijacking attack in the process and can essentially execute arbitrary code in the untrusted component. The attacker's goal is, by running code in the untrusted component, to be able to access the isolated memory of the trusted component without using a legitimate call gate, of course. So we developed some proof of concepts, 12 proof of concepts that were able to achieve this goal. By developing these proof of concepts, we came away with a few high-level observations on challenges for intra-process isolation. First, we found that because intra-process isolation is such a fundamental departure from traditional OS security boundaries, there are a huge number of possible interfaces that need to be retrofitted with new security checks to enforce the new boundaries. Secondly, because researchers and operating system developers often have such different perspectives on the security models here, it's very easy for the kernel to end up acting as a confused deputy, where it's taking some action on behalf of the attacker without realizing that it violates the security boundary of intra-process isolation. And finally, a major challenge here is a lack of a good method for systemic validation of the new security bounds, just especially because there are so many interfaces that might need to be retrofitted with new checks, and we have no good way of ensuring that we didn't miss some interface. So some examples where the kernel may act as a confused deputy. We found that the Linux developers largely envisioned PKU as being a feature for reliability rather than security. Because of this, the Linux kernel intentionally doesn't absolutely enforce PKRU access checks or page table entry read-write permissions. For example, there's an internal kernel function called getUserPagesRemote that specifically circumvents these checks on purpose. And this function is reachable through a number of user space interfaces, such as the ptrace syscall, which can read and write memory of another process or itself, as well as process VM readv syscalls, which is very similar, and the procpid-mem interface, which is a file interface that allows direct access to a process's virtual address space. So all of these interfaces could be used directly to circumvent PKRU access checks. We also found that ensuring that there are no pages that are both writable and executable at the same time is much more difficult than it may seem at first. Now, the ability to prevent this from happening is often taken as a pretty basic assumption, not just in PKU-based sandboxes, but in a variety of system security research. However, it turns out on Linux is actually quite non-trivial in practice to fully enforce. One reason for this is that page table permissions only apply to virtual memory mappings, not to whatever's backing those mappings. This means that, for example, if you memory map a file, even if the mapping is non-writable, the file itself may still be writable, and changes to that file may be reflected in the executable mapping. Similarly, shared memory can be mapped more than once in the same process or in different processes with different permissions on each of those mappings. So it may be possible to have one mapping that's writable but not executable, and one mapping that is executable but not writable. Then changes to the writable mapping will be reflected in the executable mapping as well. Finally, there are also some kernel interfaces that intentionally ignore page table permissions, such as ptrace or the procfs. So that was very briefly an overview of a few of our proof of concepts. But the high-level takeaways here, I think, are that some seemingly simple assumptions, such as no executable and writable pages, may not apply as simply as you might expect in realistic settings. Secondly, retrofitting a new security model on old code is especially challenging. So one developer's design choice might be another developer's vulnerability. Finally, all of this shows the need for a more systematic approach to validating or creating security boundaries in a complex system. So thank you. I'll now take any questions.